Next question from simple harmonic motion. So a back-to-back. However, this also requires a bit of the concept of collision. So let's see what it is. It says that a simple pendulum made up of a string of length L, bob mass, small m, you see, and that is released from a small angle theta naught. Then it strikes a block of mass capital M, and the type of collision is elastic. And the bob returns and goes up to a maximum angle of theta 1. So initially the bob had come with an angular amplitude of theta naught, and now it goes for an angular amplitude of theta 1. And we need to calculate the value of capital M. So it's something like this. See. Here, let's consider this to be the bob, capital M, and here is the simple pendulum which comes there and it strikes, and after that it goes back to theta 1. So what is the U and V? Well, U and V is the initial and final velocity of the bob just before and after the collision. So just before the collision, so that's going to be omega multiplied by theta naught into L. Going through a very simple way, the velocity is at the mean. Trying to apply the application of SHM. You can do it by energy conservation. That's fine. No one is stopping. But, it's always better to do it light-handedly. And that is all by applying the given point. The velocity at mean is omega multiplied by amplitude, and that's what we got. And just after the collision, this is going to be omega into theta 1 into L. The angular frequency is not going to change because the simple pendulum is still the same. The pendulum of length L, acceleration due to gravity is same. So you got the velocity of the bob just before and after the collision, and those whosoever are preparing for this examination, I assume they know the value of velocity before and after collision, of V1, V2, the relation. So here V is going to be M1 minus M2 into U1 by M1 plus M2. The second part will not be there because that's 2M2U2 and U2 being 0. So it's so simple now. You put the value of U and V, you calculate it, you're going to get option number 1 as the correct one. There is no difficulty even in calculation. So this is the correct option for question number 19. Now it's time we move to the 20th question. The 20th question, that's based on moment of inertia, rotational motion. Let's see what it is. It says that the moment of inertia of a hollow cylinder of this much of length is there, inner radius 10 centimeter, outer radius 20 centimeter. So let me call the inner radius by R1 and outer radius by R2. About its axis BI. The radius of thin cylinder of same mass such that its moment of inertia about its axis is also I is. We need to calculate that. So the basic idea is something like this. Let me make it with the help of a figure. So this is a cylinder here, and this portion, the mass is there because it says the inner radius R1, outer radius R2, and we need to calculate the moment of inertia about this axis. All right. So this is the axis along which we need to calculate. Well, you can do it by so many different ways, like first by taking a complete cylinder, then subtracting the smaller cylinders mi, or taking an elementary cylinder and subsequently integrating it. You can have all possible way. But yes, when you do all those things, the moment of inertia, that is going to be m by 2 R2 square plus R1 square is the moment of inertia that you get for this given arrangement. And we need to calculate the moment of inertia for another hollow cylinder of same mass, but yes, the moment of inertia is going to be same. That's a given condition. So m r square. So here's that given thing. So r1 is there, r2 is there, m is same, that will get cancelled. You solve it, you're going to get 16 centimeter. So third option is going to be the correct option for question number 20. Let's now move to question number 21. Question number 21, that's from modern physics and a very straightforward one. So here it says a particle A of mass m, charge q, is accelerated by a potential difference of 50 volt. Another particle of mass 4m, but the charge is same, and it's accelerated by a potential difference of this. We need to calculate the ratio of de Broglie wavelength. Now, that's so straightforward question, you get it here. Say lambda is h upon momentum, and that momentum is 2qv multiplied by m, because effectively momentum is under root 2km and kinetic energy being q times v, because that's how the kinetic energy has been acquired. Now here, if you just see what is the constant and what is the variable, well, this is constant, 2 is constant, and now there you need to understand even the charge is constant. So lambda is inversely proportional to root of m times the potential difference based on the given situation. So all you need to do is that you need to put lambda 1 divided by lambda 2, and you put all those values, you would get option number 2 as the correct one for question number 21. Now it's time we go to question number 22.